Hello, everyone. We are going to be presenting our proposal on a drone liquid dispersant fertilizer system. I'm Anthony Camuso,
I'm Joseph Draper.
And I'm Nicholas Pearson.
and our advisor is Dr. Gates. One second, let me switch slides. There we go. Okay, so to further define our problem, I wanted to provide a little bit of statistics and background information. So the three main fertilizers that are used in the US are nitrogen-based, phosphorus-based, and potassium-based. And the application rate since 1960 has been increasing. It's actually increased almost 200% from 46 pounds per acre per year to about 135 pounds per acre per year. And this is substantial because about 40% of the entire land in all the United States is farmland. And of that, about a third of it is used for crop production. And then about a third of that is actually treated aerially with fertilizer. So you could see how this could be a big business. And it is. There's 1,500 companies that will come and provide this service for farmers. And they're pretty expensive because their aircrafts range from nearly 100,000 to $2 million, and the average pilot has about 19.4 years of experience. So it's not something that you could just, jump in a plane and go fertilize your crops aerially yourself. You need to hire someone unless you have a pilot's license. And these are two methods of how fertilization can be done aerially today. Either typically there's a helicopter used, and you could see the sprayer heads right underneath the cabin there. Um, or you can actually use an airplane, and you could see the sprayer heads right underneath the wings. Um, these are both called crop dusting. So our proposal, the problem we want to solve is we want to make a cost-effective, time-saving solution to the process of fertilization. We want to make it user-friendly so that anyone can pick it up and do it. So what we're going to do is we're going to develop a liquid dispersant fertilization system for a drone that will be provided by Dr. Gates. Um, and our goal is to make this drone have nearly autonomous operation. So after you program it for your set of land, you could just let it go and spray the fertilizer, and all you'd have to do is recharge it and refill the tank. So in terms of some design constraints, flight time is one of them. We want the drone to fly for at least 10 minutes. In terms of weight, Professor Gates told us that his drone could carry up to 20 pounds of weight. So we're limited in that respect, but he said it could increase. He's not really sure yet, and he's going to give us a more accurate figure later on. For liquid inertia, the tank, the fluid in the tank, if the drone were to make sudden movements, it could potentially throw off our autonomous system. So we need to control the fluid motion. And one way that we thought about doing that was with baffles. The tank size has to be uh, proportioned accordingly because we don't want the fluid to run out before our 10-minute flight time is up. In addition to that, we're going to have to limit the number of nozzles because there's simply the way that the frame that he described the frame to us. We're not really sure where we can place them, but the idea is that we want the nozzles to cover the entire drone area underneath it to make sure that whatever's underneath it will get sprayed and it will have full coverage. The nozzle position is going to be adjustable because we're going to use servo valves, and that's important if it's on a windy day. Um, Modular design just basically means that we want the system to be fully removable. The drone can be used for other purposes. The location of the apparatus is important because we want it to locate it close to the center of gravity. And I already mentioned about the spray area. We just want it to cover all the way underneath the drone. In terms of material, we want the material to be as lightweight as possible because Obviously, it's a drone, it's flying, and any extra weight is going to cause energy losses. We also have limited manufacturing because we're going to use either the labs at CCSU, or we have access to a 3D printer via one of our friends. And then we're going to do some testing on the drone for functionality and performance. And we have to have this completed by December of 2020. So the people that we thought we could target this to were the small scale farmers or the landowners. And the reason that I say small scale farmers is because the drone frame is preferably an 8x8, 8 foot by 8 foot. So it wouldn't be ideal for spraying a lot of crops, but to the people who mainly do this by hand or with machinery that needs to be constantly, you're doing monotonous labor and you need to always pay attention to it. This would be a really great option for them. And in addition, landscapers do this all the time where they'll drive to properties and they'll spread fertilizer. This would be great for them because it would save them time. They could devote it to doing other things while the drone is simply fertilizing.
So in terms of research, one of the avenues that we looked at was analyzing past or existing solutions. The agricultural industry has really focused on technological advances to improve production while maintaining their quality. Current methods, as said before, were helicopters or planes with the large-scale rig nozzles for fertilization, spraying pesticides or crop dusting. Some of the major problems, though, and the reason for our design or plan is to have a reduction in the amount of cost for flight and making it an easier access for individuals who are for landscaping or small scale farming. Because some of the costs reach up to at a minimum of $1,500 per hour of usage. So when looking at past solutions, drone application was a big one, and we focused on 3 drones in particular. So the first one is the airborne agro drone. This one is probably the biggest competitor that we've noticed and that we would be competing with. Some of the pros include having a larger scale coverage, so for larger scale crops, having a higher capacity and spray distance up to 33 feet. But one of the bigger other problems is that it's very heavy, up to 330 pounds with a low flight time. So ultimately, this would not be beneficial for small scale farmers, which is our target consumer. The second one is the DJI Agris MG1S. This is mainly located in Asia and is very recent for design. It's only been out in the market for a short period of time, and not too many people are familiar with it. But over time, it'll definitely expand. So we consider that to be another competitor. It's very light in weight, up to 30 pounds, with autonomous control, so which is beneficial to small scale farmers or individuals who aren't familiar with controlling them or manually operating them. But some of the cons or negatives to this design is that the coverage is very small. The capacity of the liquid is only 10 liters, and it has a low flight time. And then the final design was the Yamaha R Max drone. So this one has a longer flight time, up to an hour. But some of the other negatives is that the capacity is very small, the coverage is not that great, and the weight is significantly high. So definitely those statistics for each of the designs are things that we hope to accomplish and improve in our design, as specified in our design constraints. And although these designs are very different, they have many drawbacks. So that's why we are considering improving this process.
Okay, so now we'll talk about us. We'll just talk about a little bit about our strengths and weaknesses. I'm Anthony Camuso, so in terms of my core strengths, I'm highly conscientious, I'm organized, and I'm hardworking. The main topics that I like to work on that I'm good at are thermodynamics, fluid mechanics, heat transfer, and machine design. And I have a lot of experience assembling mechanical devices, such as like rebuilding engines. Um, in terms of weaknesses, I don't like to work in teams, so this is going to be a challenge for me. I tend to get stuff done very quickly, which can be to my detriment at times, and I don't find myself to be that creative. Um, in terms of knowledge, I don't know much about manufacturing processes or machining, and I don't really have much hands-on experience doing that.
All right. I'm Joe Draper. My strengths, I have a determined work ethic. I like to think I'm organized, uh, great time management skills, and very creative. The classes that I enjoyed and the or enjoyed are statics, dynamics, fluid mechanics, machine design, and physics. Technical skills, great working with my hands, milling, lathe, injection molding. Weaknesses, I can find myself being overly social. And also a weakness of mine is thermodynamics and heat transfer, but I've not taken heat transfer yet. And my technical skills that I have weaknesses in are welding methods, NX, and ANSYS.
So again, I'm Nick Pearson. Some of my strengths: I'm very ethical, an effective communicator. I enjoy working with groups and listening to other inputs from other team members. Um, some of the classes I've taken include machine design, manufacturing processes, thermodynamics, and fluid mechanics, which can be very beneficial to the senior design course. Some of the technical skills are include but are not limited to SolidWorks, ANSYS, and MATLAB. Aside from SolidWorks, I also have experience using Autodesk Inventor as well as NX. In terms of weaknesses, I'm very indecisive when it comes to decision making. So at times we could be at a stall and it'd be difficult for moving forward. I get impatient often when deadlines are not met, and sometimes procrastination can come in, as well as creativity. In terms of knowledge, I haven't taken heat transfer yet, but I have taken thermodynamics, statistics, and materials analysis. I'm currently enrolled in, so I'm actively learning and eventually be able to apply it to this course. And then for technical skills, any non-traditional machining such as 3D printing, EDM, or CNC.
All right. For pre-tasks, we had to interview potential advisors, which we have come to an advisor who is Professor Gates. Also, brainstorming topic ideas between groups. That took us a little longer than expected, but we have come up with a idea. Develop product specifications. This is in order to figure out what we need to manufacture and purchase for parts on our drone. Create a Gantt chart, which has already been completed. Analyze past and present solutions, and complete the safety training, which is a little conflict with this coronavirus. Not having access to labs, but that's besides the point. Develop progress reports, documents, and presentation. Develop portfolio for project, and that That'll take the most amount of time, which is about 40 weeks. So the end of next term. We also need to develop a prototype. And also a briefing before the summer to discuss tasks and figure out what needs to get done during the summertime. Let's see here. So our tasks category, the first one is research. So we need to acquire a CAD file from the drone frame and brainstorm possible locations for the mounting platform, tank, and nozzles, motor, etc. We'll most likely be using SolidWorks to be doing this to 3D print our tank and mounting system. Determining which parts are going to be necessary. That is going to take about 2 weeks or so. Distinguishing manufactured parts from purchased parts. That is basically creating a bills of materials to distinguish purchased and manufacturing and costing of materials in order to have a better overview of what needs to get done. Next we have design. So the first thing we had to do was brainstorm solutions and ideas for the liquid disbursement system to be attached to the drone frame, which will take about 3 weeks, and that's done with the group. And we'll be selecting a design using a decision matrix. Designing the mounting system and tank will be done with AutoCAD. We decided the tank configuration should be rectangular. And also we need to make sure the mounting system is safely secured to the tank along with the tubing and spray heads. All right. For analysis, we need to perform an engineering analysis with calculations on flow rate of the nozzle, pressure requirements for aiding in the tank design. That should take about 2 weeks. And also perform an engineering analysis of liquid within the tank and nozzles. That'll be done using ANSYS Fluent. Estimated time for that would be about 2 weeks. And the primary is Anthony and secondary is Nick. Manufacturing. We're going to be manufacturing the tank and mounting system. We will use outside processing to 3D print the tank, as it will be made of some sort of plastic that's preferably going to be clear or see-through. The 3D printer model that we will be using is the Alternator Creality CR10S, and the platform for that is a 13 by 13 by 15 inch platform. So we'll have to make 2 halves of the tank and then put them together. And the material we will have to soon decide. We'll need to have the ability to securely hold the chemical compound of the fertilizer that the drone will be holding and dispensing. Any metal work done will be done at CCSU and the Copernicus Labs. And we are assemble the liquid disbursement system on the drone frame. And that so the assembly of that is going to be done by Anthony. Let's see here, testing. Testing the system for functionality and performance with the aid of Dr. Gates. All the testing will be done at CCSU. The wind tunnel may be required to test the drone for stability in high winds. Troubleshooting will be occurring throughout the whole process of our design or of our project, and that will most likely occur during design, testing, and also data analysis. And then the finalization is perform data analysis from testing using software such as Excel and Minitab to develop conclusions of the performance of liquid disbursement system, and to write our final report and presentation on all the information recorded throughout the project.
So for the tasks completed, we selected our advisor, Dr. Gates. Took a fair amount of time to complete. It was a tough decision as it would sort of drive the entire project. We chose a topic, which is the fertilization of crops using drones. That was another big or long task to be completed. It sets up everything going forward. So it's very important to make the right decision on what we're going to be doing. We developed a Gantt chart, so listing all the tasks was fairly easy, and putting it together using an aided software limited the amount of time we would spend developing a schedule. Research has been going on and defining the problem since the beginning of the project, so approximately 54 days, as well as analyzing past and present solutions. And then safety training, which is to work in the labs. That was since the beginning of the semester up until a week ago after spring break. Yeah. So for the timeline or chart going forward, we plan to begin developing a portfolio that will continue on until the end of Senior Design 2 by defining the problem, developing specifications, research, and continuing past and present solutions. We also plan on creating a conceptual prototype by the end of this semester due to the limitations and unforeseen circumstances. So that might include redesigning our schedule and doing brainstorming solution ideas, as well as selecting a design, as well as also looking at functional components for the drone. And this is a picture of our Gantt. So all the tasks are listed with designated. This is a rough draft of what we will be following for this and next semester. Each task is indicated with a specific color, yellow being for the group, designated colors for each individual who's the primary leader of that task, and then the individual is mainly for the safety training. So right now we're about 25% complete, and we feel that we are on track to meet our deadline for this semester and the following. So in conclusion, as stated before, we feel our group is on track developing our liquid dispersant fertilization system based on what we have already completed, as indicated in our Gantt chart. And as mentioned also before, due to recent changes in the structure of the course, meeting lab access will have to be reevaluated by our group, and definitely changes to our Gantt chart will be required. In order to complete the remaining tasks and going forward, we will continue to have constant documentation in our engineering notebooks to have proven documentation, as well as continuing research and generating ideas that will be beneficial for our portfolio. We will also be discussing with the other group developing the drone frame over time to see where they're at and how that will affect our scheduling. And we will continue delegating tasks and meeting deadlines up at the end of the semester. Any questions?